All right, so we can get started. Hi, everybody. Thank you for coming. Welcome to our webinar series. So my name is Kate Cahill. I am the PI of the Computational and Data Science Exchange project, which recently started. And our goals are, to share computational and data science curriculum, both curriculum that we've created, that the members of the project have created, but also kind of bring people together to share other materials and also to develop new materials. So this is an ongoing project that we'll be doing other activities over the next few years to try and bring together a faculty community and help people do more computational and data science in the classroom and develop new materials. So right now we're doing this webinar series as one of the first activities in our project. This is our second to last presentation. So today, Alam Tanouri will discuss the course that she developed at Morgan State University as a member of our pilot project, and she's also part of our ongoing implementation project. We have one more webinar after this, so next Friday will be another project member of ours, Dina Tandabani, will discuss doing computational chemistry and biology using science gateways. But today we're going to talk about matrix methods with Dr. Tanouri. So Alam, it's all yours.
So good afternoon, everyone, and thank you for taking time this Friday late afternoon to share with us what we are doing with the CDS Exchange. So maybe you have an idea what's happening with our project. We are trying to develop courses, and of course, for data science, and we're going to squeeze as well machine learning. And we would like to disseminate what we do at each institution that are part of the grant. So the idea is, to share, to disseminate, and at the same time, to learn how we can improve whatever we are doing. So your input is very, very welcome. So my name is Alam Tanouri. I am from Morgan State University. And recently, in the last couple of years, we have a course. I am from the math department. And we have a course, and the course is, people who already took introductory linear algebra. The second part of the course was like advanced linear algebra. So at one point, we started to think in the math department, we would like really relevant, and we would like to show the students. So what you did in your course, introductory linear algebra, we're going to use it and to show you that, most of the mathematics that everybody is boasting about, like machine learning, we did that, we do that. And a lot of topics, they are from a linear algebra course. So because I know that as a core, my power presentation will be disseminated by Professor Cahill. I introduced more things to tell you what I do, but it's going to take a lot of time for me to go through that. For example, what I am sharing in my PowerPoint, but I might not spend much time on that. So my course description, what do we do in this course? And you are welcome, once it's shared, to read more about what's happening. So in a nutshell, what I am doing, I'm taking most of the algorithms, and the computational methods that students learn in linear algebra, and we are going to give it alive. A lot of work that I'm going to show today is based on eigenvalue, eigenvector, and how we can use them. There are methods that I'm going to mostly spend most time on it is singular value decomposition. And the algorithm, from what I noticed, most introductory linear algebra don't tackle the singular value decomposition and PCA, principal component analysis. So I don't know if you had a minute. I know we have we have only 2 minutes per slide, they say. But if you had a minute to read it, it's okay. Please don't feel like I am rushing, because the objective is to have it available if you are interested. So here I'd like to say that in my course, I rely a lot on using MATLAB. So when I start the course, I make, and you're going to tell me MATLAB and money. It happens that our university, we do have a license already for 10 years or so that is available for every single student at Morgan State University. And I started using it, to teach in the engineering courses. So where I start with making everybody take an online ramp course, introductory to MATLAB. You're going to tell me about Python. We'll talk about it. I'm not too good yet with Python. I feel very comfortable with MATLAB. And professors, what they do, what they are comfortable with, they make it, they deliver, to students. So I make the students take a course in MATLAB. And at the same time, I will send into my syllabus what the students should know before starting to take my course. And this is the basics that everybody taking my course should know. I'm not going to read through that. And what is the course goal? It's to introduce the students to advanced topic from computational linear algebra. Let me push this one a little bit. Give interpretation of matrix operations in the context of data. Apply matrix decomposition. This I am in love with matrix decomposition. All the algorithm of matrix decomposition, starting with matrix factorization, and we are going to use them to build tools. I am not here to advertise using MATLAB, but MATLAB developed a lot of nice courses that I am using and recycling. And I would like to say I didn't invent any of the works that I am writing here. Mostly it's recycled. I read it, I prepared it. So I try to put references every time. But when I am going to release it, I will make sure that everything I wrote on my presentation, it's referred and to the right sources. So what we do, we're going to use software to analyze a real-world problem from various fields, make prediction, and use result for training. This is important for training and discovery. So at this point in my course, what I am doing, I am trying to, get it ready for training. If we are going to train, we would like to have features. And how do we get these features to start training our data to do the machine learning algorithms? So what are the learning outcome? These are the learning outcome. Again, because it is going to be posted, I would like you to take time, if you like, to use whatever we did, in your classes, or take modules from your classes. So I would like right here, maybe to give you what I do in class with these things, singular value decomposition, principal component analysis, examples, and so forth. I'm always worried about running out of time. As I said, I am in love with matrix composition. I would like maybe, if I have time, to talk a little bit about clustering algorithm, support vector machine, and maybe more about dimensionality reduction techniques, singular value decomposition, and principal component analysis. So the applications, there are tons of applications. I cannot do them every semester. I can do maybe, I first introduce so many topics and I give them examples. And after the midterm, I start talking to the students into one-to-one, to tell them what is your interest. And so far you learn a couple of algorithms. What is the topic of interest to you, to your majors, that you would like to investigate? So every semester I do have students that come up with something, some of them, because we'll talk about that, health of cities, or crimes in the cities, or data, all kind of data set is of interest to the students. They come up and we try to identify, for example, if it works. Recently, you know, in the last couple of weeks, somebody came and tell me, oh, I would like to see biased in, you know, in image recognition, you know, the bias. So this is something that I didn't develop yet with the students, but we will be working on it maybe during the summer and next semester as well. So based on what we do, again, this is not a graduate course yet. It is an undergrad course. So it's good that we wetting their hand to start thinking beyond what we do in the class. So when I teach the course, you know, these are the modules that I have for them. You know, I divided them on 9 modules, but they can change. And, you know, first week, second week, 2, 3 weeks, you know, if you are interested to have an idea, you know, how much time I spend on each topic. Okay, what is machine learning? I am not sure if everybody attending, you know, like you might be expert, you know more than me if you want, but some of you are not, are coming from social sciences, because I know other people are starting to get really interested into getting their data from any field. So machine learning teaches computer to do what comes naturally to human, learn from experience. I didn't invent that sentence. Most probably I read it somewhere and it stuck in my mind, and I am using it. So this is what I like, you know, learn from experience. We are teaching the machine to do that. And in order to do that, we use 2 general type of techniques. Maybe there is more: supervised learning and unsupervised learning. You know, the idea of unsupervised learning, you know nothing. You are in front of this data and you have no clue what's happening. First thing we would do, imagine you see all the students the first day of school, you know, listening to the president give a talk, and you do have everybody inside the auditorium. And you have no clue, you know, who are they? So the first idea in your mind, you would say, oh, these are the freshmen, these are second year, these are computer scientists, these are mathematicians. So this is the idea of like unsupervised. We know nothing yet, and we would like to describe characteristic to classify them. So this is a picture image that I like to use in my syllabus for the students when I tell them about machine learning. So this is the part that we will be covering, the linear algebra. You know, of course, there is the statistics, multivariable calculus, and optimization to build the skills for machine learning. And actually always, you know, when I have an image that I took from somewhere, I do have the reference right here. And again, I talked about supervised and unsupervised learning. We have here classification and regression, and we have a clustering for us to do the work in the classroom. I think at this point, you know, these are simple definition of what is supervised learning. What do we do? The classification techniques predict categorical response. For example, this email, is it a genuine or a spam one? A tumor, is it a characteristic? It is a cancerous one or a benign one? So these are the classification technique for supervised learning. And we do have the regression technique. We do have all kind of regression. You know, like we teach, speaking, I use matrices to teach them, but some people already had an idea from statistics a little bit about regression. The unsupervised draw inference from data sets consistent of input data without label response. Okay, as I said, you know, we don't have a particular pattern. Let's say I have weight, and I have you know, like weight and I would say length, and I have all the data posted all across about weight and length. And let's say these are, or sometimes we talk about bones, then bones, you know, girth of bones, etc., and date. So we have data from all over the places, and we would like to classify them, maybe the lower end, the middle end, and etc., etc. So these are some of, I am rushing through some of them because these are the subtopic of what we talked about, classification, regression, clustering. The fourth pillar of machine learning, the first part, we represent numerically the data using vectors. And this is where linear algebra comes to play a role. And after that, we giving two vector, for example, representing two objects in real world. When we talk about object, for example, I take an element and I would write all the characteristic of this element to classify that. And in the third part, we do matrix decomposition. And in the fourth part, we do some classification, and in the context sometimes of support vector machines. Okay. I would like to tell you how I start teaching singular value decomposition for my students. Before they do any of that, they have to learn, or they have to know how they can find how to multiply matrices, of course, how to find eigenvalue, eigenvectors. And, you know, to make sure, this is something that I do in class, and to make sure that they know how to do that. So, for example, this is an example that I give them. I tell them to find the singular value decomposition because my objective is not the calculation only. MATLAB can give me an idea how to do the calculation, but mostly I teach math major or engineering. I would like them to have an idea what is singular value decomposition mathematically. It's not falling from the sky. It has, you know, it is based on eigenvalue, eigenvector, etc. So what do we do first? You know, I like to do my presentation. I can make it a little bit bigger. So this is an example exactly that I give in the class to make sure that students know how to find these eigenvalue and eigenvectors. And once they practice enough, I tell them, you know, we are not at the introductory level. We would like to use it to do some kind of machine learning. So I will make them go to MATLAB, or if you want Python or whatever it is, to once they have the data represented in a matrix, we would like to find what is the singular value decomposition. So, of course, you know, to do that, they have to know how to multiply the matrices, A times the transpose of A, find the eigenvalues for when you do A times the transpose of A, and again, they have to do A transpose times A to find the eigenvalue, etc. I didn't go through all of it. I have it somewhere in my Canva, but this is the technical, I don't want to say technical, hands-on work the students should do before I start giving them an idea. Why do we use that? So this is something that I remember, I recall, I don't know, maybe 10 years ago, I was fascinated by this example, and I use it after they do that. I use it to highlight the importance of singular value decomposition and how we use it to deal with data, especially with large data. And at the same time, how we can simplify the data to get all the relevant information without junking the system with all the data. So okay, let me do presentation mode here to maybe we can see it a little bit better. Oh no. Okay, so first thing, then they know already how to do singular value decomposition by hand. They were trained to do SVD, you know, in MATLAB as well. And first application, how do we do noise reduction? So I give them here, and oh gosh, every time this is what I don't like, sorry. I like to keep it this way. So in this case, okay, so I hope everybody sees the rectangle, whatever it is, image that I have right here. So my first question would be to the students, You know, like, what do you see in front of you? They say, oh, they see a rectangle, they see, etc. My second question to them would be, you know, this is 25, 25 rows, 15 columns, etc. And if you look at it, how many kinds of columns can you see in the picture? I can give you a minute. How many kinds of columns can you see? I don't know. I would like if somebody would answer. I don't know if they can answer, but it's not important. How many kinds can you see of columns? Okay, I don't want to put anybody, but this is what I keep it for a couple of minutes at the board, and I would ask the students to do that. And some of them would say 4, some of them would say 5, you know, etc. So I would look at this and I say, we do have all white columns, a couple of them here, a couple of them here. This is kind number 1. And here, what do we have? We do have all white, all black, all white. So this is the second type. The third type would be white, black, black. And the third type, it's repeating right here, and it's all white. So how many types do we have? We do have 3. The all whites, the ones that is alternating 1 time, and the ones that is alternating 2 times, black, white, black, white, black. So how many types of columns do we have? We do have 3. Of course, already I trained the students, you know, somehow to take the pictures that they have, or they don't have to do it by hand. They can do image read in MATLAB and transform a picture into a matrix. So how can we transform it? We can transform it by coding here all zeros and here all zeros and ones. We can do all ones here and all zeros here. So this is what we can do to try to use the computational, you know, capability of linear algebra. To do what? To find out how we can say and simplify. Imagine you're going to go to Home Depot and find and buy these kind of tall, I would say, piece of wood per se. Well, how many kinds you're going to buy? You can buy this kind, and this kind. You're going to buy only 3 kinds, but a couple of these, a couple of those, a couple of that. So we would like to simplify what we are talking about. We are talking about 25 times 15. I don't know if I know how to multiply 325, 375, 325 data we do have on that image. So look now. I showed you that this is what we have. Let me make it a little bit smaller. So we do have 3 kinds. This is the kind we are building, and this is the matrix associated with it. If I make it a little bit bigger, you can see it. It's representing the same color. If you want all ones, all whites at the very beginning, you have white, black, etc. So now I can take the matrix, I can read it in MATLAB, because I cannot do singular value decomposition by hand of, you know, 375 or 15 columns. So when we do SVD, I wrote it somewhere, the command. It must be here, you know, like here is the command simply that the students write, you know, when they enter the matrix, SVD. So when they enter that, they find that they do have 3 singular value decomposition. 3, you know, sigma 1, sigma 2, and sigma 3. Oh, you know, so I associate the sigmas, which are the singular value decomposition, to the 3 different features I do have in my image. And now the matrix M that is like this, so complicated, I can write it as the sum of 3 matrices. So far, all what we did, we trained the students to have this image, to read it and write SVD, but they know how it was calculated. This is the matrix M times the transpose of M, find the eigenvector. Actually, we call them a singular value decomposition because we're going to take the square root of whatever. So this is the mathematics of it. And I would like here to emphasize the presence of the 3 singular value only. you know, like we have that. So now I hope, because sometimes in some cases, when I do some kind of lecture, some students would say, you know, they cannot see it. I have a picture in front of you. I don't know if Professor Kate, can you tell me if you see only white and black or you see something else?
I mean, I definitely see shades of gray in the white.
Okay, thank you. This is what I want to say. This is an image that resembles the other one, but it's not, because you do have the gray. When I'm going to read it into MATLAB, I'm going to have other numbers, 0.98, 0.97, etc., etc. So if I ask the students how many different columns you're going to have, so they are not going to say anymore 3, you know, based on what we did before, because first column and second column and third column, and you know, they are all different. If you look at 1 and 2, this one has more gray. I hope everybody can see it. I don't know, I can make it even bigger. If you you know, you can see better that. So now I'm going to enter it, not by hand, you know, like I'm going to make MATLAB read it for me, and let me make it smaller. I'm going to do MATLAB read it for me, and after that I want to do SVD, singular value decomposition. So how many different columns we think we have? We're going to have 15. And if you see right now, I don't have only, you know, like 3 of them. I do have 15 of them. This is a result of us running this in MATLAB. So how many singular value decomposition we have? We do have 15 of them. But most of the time, you know, maybe I didn't say that, when we do singular value decomposition, it goes into decreasing order, you know, so we start by the highest one. This is how we get them, lowest and lowest and lowest and lowest. If you take a minute, sigma 1 is 14.5 relevance, but sigma 15 is 0.05. So right here, we're going to see that these vectors, you know, like the sifting through the singular value decomposition, is going to tell me there are important ones and they are non-important ones. So for example, 0.05, we can think about it as a noise and we can get it out. So when I factor the matrix, I'm going to factor it not using the 15 of them. Maybe I can use 4. The best way may be to use 3 or maybe use 6. You decide. You decide depending on what the precision you are looking for. But definitely we are going to think about 0.05, 0.19. They are not relevant, and most probably to clean the image, it was supposed to be all white and black, but it's not. The question the students would ask, what if it was like this? If it is like this precisely, okay, I leave it like this and I don't run the singular value decomposition. But don't forget, for us, we are classifying things. So whenever we do have some kind of junk around, we would like to clean it so we can go through the classification and train the machine into clean images so that we can find out. So one of the students, this is some work done by one of the students. Most probably you are going to look and you're not going to see anything, because what happened when we do the composition here, when we do the, let me get here, when we do the composition here, we can use 15 singular value decomposition, we can use 3, we can use 4, or we can use 0. If we use 0 singular value decomposition, we get nothing. You know, right here, I am using singular value decomposition. I get nothing, you know, because when I simplified, it went to dark. If I use 5 singular value decomposition, you start to see shadows. Can you guess the shadow of what it might be? You don't have to answer. I'm sorry, just I am in the mood of teaching most of the time. I apologize dearly. So we cannot see much. But I see there is something here darker, and this project, it's not my handwork. It's the students, one of the students, she did the work. So look, now we can see a little bit better right here. We can see that we have, most probably we are talking about, you know, like if I see here, we use 30 singular value decomposition. So the image here, it has, I don't know, 750 columns or you know, like it is large. We are going to use only, we would have, I don't know, 750 singular value decomposition or whatever it is. We're going to use only 30 singular value decomposition. And because most of the time I'm teaching, you know, math and engineering, I would like them to plot, you know, the error between the compressed image, this is a compressed image, and the original image. This is important for me because at one point, there is no need to use 50 singular value because imagine we do have 400. At one point, we're gaining nothing with the error. We're not gaining anything. So if we have 0, you see the error goes to infinity. If we use 10, we're okay. We use 20 is better. We use 30 is better. There is no need to go 70 and 80 because we're not gaining much to recognize the image. So there is no need to junk our system with all this data. And by the way, this was the original image, and MATLAB can only deal with it because we can go from RGB to gray scale for us to run the singular value decomposition. I don't know, students like that one when I share it, but it's one of the students who did that, not me. I mean, it's not really, I don't like to do it, but we're good. So once I finish, oh my God, how much time do I have? 6 minutes?
I mean, 20.
Because you said we have to leave time for people to ask questions. Okay,
Yeah, I mean,
so I know myself, I talk a lot. So once we finish and we practice and they are enthusiastic about taking pictures of their faces, taking pictures of themselves, of something of interest to them, and run the MATLAB program. I'm not going to say, you know, it can be done easily. Because here we have to run really a program, you know, using loops to find out, you know, the computation of the error right here, you know, to produce the graph. To produce a graph, we have to do that. And I am jumping quickly to talk a little bit about principal component analysis. Okay. Once they learn the technique of doing singular value decomposition, we move mathematically to create a matrix, and the matrix is going to be finding relationships. And to find relationships, we talk about covariance. I don't know. It's not hard for people who didn't do statistics, but everybody knows variance, covariance. But if 2 or 3 students don't know anything about covariance and variance, you can take them apart, or you can do a 10-15 minutes explanation about the covariance. So we have our data, and to apply the principal component analysis, which is dimensionality reduction, you know, algorithm. So what do we have? We have to create the matrix of the covariance. Then once I have a matrix of the covariance, I'm going to run singular value decomposition to reduce dimensionality. So principal component analysis would tell me which 2 components are really related to each other. So there is no need to consider them if they are the same. So if I am talking about weight and I'm talking about the price, and I know what is the unit price, there is no need to have a column of weight and the column of price because they are proportional. So we are not gaining much information. So what we are going to do, once we find the covariance, we are going to do the singular value decomposition, and we are going to chop the sigma that they are smaller. Here I use as an application to principal component analysis. I use an application from, I'm not here to advertise MATLAB, just it happened like the way you use Python, I am using MATLAB. So they do have a nice application that it says, that analyze the quality of life in US cities, you know, and they use PCA. So I make the students go through the example, and sometimes because, you know, one idea would be, I would like to talk about, you know, social impact, not only teaching machine learning for machine learning. So this would be a subject of interest to people about quality of life. And when we talk about quality of life, we have to define parameter. What is it? You know, temperature in the summer, temperature in the winter, crime, school, you know, parks, etc., etc. So this example, and I hope I can copy it and I want to run it. I don't know. I want to see if I can run it. Give me a second, please. I think I have it ready. Okay. I already prepared it. So this is the MATLAB documentation that I tell the students to go to. You know, first you have to load a sample data. The sample data is already ready-made in MATLAB examples. So first they have to go through that, you know, run it themselves, etc. And after that, they have to create their own, you know, but this is a very good example that I like a lot. And the category given, it's about the climate, housing, health, crime, transportation, education, arts, recreation, and economic. So we do have all these factors, and we're going to determine which one is the most critical for us to determine. So you're going to tell me all of them are very important. Maybe for some people, crime would be number one. Maybe for some people, arts would be number one. For maybe people who are retiring, they need recreational. You know, people who retire, for them, economics is not really factor number one. I don't know. So we take all the data, and you know, like I can write right here in the chat. I can write in the chat if you are interested in looking how it is run, to show there are many applications to show the importance of. So I make them go through all this training to determine which one is the most important. But once they finish, they have to do their own work. So let me go back to my presentation if I can find it. Hold on 1 second. Okay. And I will write it in a minute in the chat. So this is one example of using singular value decomposition, or PCA. Okay, this is new. I told you this is new. I taught the students about clustering, and you know, and at the same time, we talked about k-means. There are several. I think only in my class I do have only time to talk about k-mean. And you know, here this is an exercise that I found somewhere. Sorry, I don't remember from where, but I know I recycled it in the old time and I use it. So here, once I showed them how to work on clustering and etc. Actually, here we do have 4 phases, and darkness or the number of dots would represent density, you know, of colors. The line, you know, the lines are not important. You know, don't think about lines. Think about colors, because the colors is making the line. So if you look at the line here, I'm not interested into the line. It's pixels. And I'm interested into like dark pixels, white pixels, etc. And this is how you can find the cluster of eyes and nose, etc. So here, when I talked about that, a student recently started to think about the bias in facial recognition and how can you use some of these concepts to work on that. So we are starting to work on that. What else do I do? Oh, this semester I didn't do. Maybe 2 semesters ago I did. You know, optical character recognition. You know, so if you have an image, how can you make, you know, the software try to, you know, recognize from all the image the writing? And, you know, like I should have the number 3 somewhere. Yeah. So you see how we can recognize, you know, like sometimes, not sometimes, some place we do have, you know, the number, I don't know, like, sorry, just let me see. Oh, oops, I should have prepared a blank page. So for us, when we talk about optical character recognition, I can write my number 3 like this, or I can write the number 3 like that, or I can write it like this, or I can write it even bigger, you know? So when we talk about image recognition, we do have a dictionary already, is that something that looks like this, And how do we do that? We do feature extraction to recognize this might represent the number 3. And, you know, again, the A, how do we write the A? Some people will write the A like this, you know, so we have a dictionary that can already recognize these images. And this is how we can sift through and recognize that this is the work. Most of the work I got inspired with across the year, you know, like most probably this might be MATLAB. I'm not sure anymore, because I've been doing this for a long time. And you see, like all of us, you collect on in a folder tons of information that you say one day you like to use. I think I would like to leave some time for people. I'm going to rush through that. The students are fascinated when I teach singular value decomposition. When I teach singular value decomposition about the use of kernels, it's hard, and sometimes students don't understand it. You know, so the kernel in general, you use it a lot, not only in machine learning. But if I want to classify this data, this is 2-dimensional, and I don't know how to classify it. So what do? I bump it up. You know, I take it up, I take it to 3D. And once I take it to 3D, we see that we do have 2 different clusters. So to do clustering sometimes, and, you know, like when we talk about support vector machine, most of the time we would like to find a line, like a straight line, that separate between my data. I cannot find, and I hope you can see my cursor, I cannot find a line that separates my data. You know, like, or a plane that separate my data. So what do? I bump it from 2D to 3D, and now I can find a plane to separate my data, and I can cluster my data that way. So I hope that I didn't rush much. The references are right there. I will give the presentation to Professor Kate. And if I need to adjust some things, I will do it, and she will post it, I think, very soon. So this is the things that I put for my students, you know, in my syllabus: have a good semester and work hard. This is what I write, and they would ask me, what are these? I say, during the semester we would learn what's in that. The question, just I added it now, and thank you for listening to me.
All right, thanks a lot, Alam. So anybody have any questions about anything that Dr. Tenori shared, or about the course in general, or any other things in the project? You can unmute and ask questions, or type them in the chat.
I don't have any question. This is Sajid Hussain from Fisk University. But thank you so much. Awesome lecture. You are blessed with the gift of explaining so nicely, especially the single value decomposition. You very gradually you built up, and the examples you gave for this pattern recognition. This is a really nice example. You're a very good teacher. And
yeah, actually, thank you. It makes me feel good, because at one point a couple of years ago they gave me the award of being the best teacher. Now I am hosting among math, physics, chemistry, etc., etc. So I got an award because they say I am gifted with teaching. So they make me teach the engineers, because they tell me I can explain these math concepts to engineers. So thank you. I shouldn't have said that. Sorry, I apologize. I am a little bit worked up because I am doing the presentation. Sorry about that.
I also like your slide of having a machine learning in the center, and multivariable calculus, linear algebra, all the tools which are needed. Sometimes we do data science and we think that those other information is not needed. That was really insightful site. I really like it.
I appreciate a lot. You made my day. Thank you.
There's a question in the chat. What are the minimum requirements for students taking this course?
Introductory linear algebra. So they have to know how to find eigenvalue, eigenvectors. You know, of course, you start basically, yeah, you know, once students know how to find eigenvalue, eigenvectors, they can go ahead. And some professors, from the university, they are approaching us to do what I do for social sciences, for people who we can equip them for some kind of software. We explain to them what is an eigenvalue, eigenvector, with basic knowledge of matrices, what they are, what they represent, so we can reduce it and we can equip a lot of people using the software to use machine learning. They don't have to be mathematician, but for me, I teach a math class, so I would like them to know, how to produce some work by hand, multiply, divide, get it by hand. And after that, I make them go use ready-made software like MATLAB and other things too. And Python, sometimes some people insist on using Pythons. It's okay, they can use it. But, this is a disclosure. I am not too strong. When they make an error, it makes me time to really find it. But I will work on it maybe this summer.
So do you have students from a lot of different disciplines?
Yeah, I have students from biology, but they have an idea about matrices. I have students from chemistry, and I do have students from engineering. They take anyway engineer. So to the person who asked, you can reduce your course. I think, I didn't try it. I have to test it one day to see if we can downgrade it. And this is what the university, a couple of professors at the university level, they had an AI workshop with Deloitte and everybody like about 2 weeks ago. And they were asking me personally, if I can develop a course, at a much lower level, but equip the students with the capability of especially social sciences and psychology and so forth, to find like the health of the city. Everybody can benefit from that, like in the social sciences. They don't have to be like mathematician to do that. I hope I answered the question. So technically, for me, they have to know up how to do the eigenvalue, eigenvectors. If they know up to that point, I think I will be okay. Should I read the chat? Okay. Okay. Thank you.
Yeah, so there is another question about what are the types of coursework that you have the students do? Is it mainly project-based, or are there other types of coursework?
I give them, because mostly I think they have to know the background. First step would be low-level practice problems, like matrix 3x3 or something. So they have to reproduce whatever the software can give them for large matrices. They have to reproduce it by hand. So yes, first I give low-level homework, and after that I tell them what is the objective of what you are doing. And at one point, I think I forget totally, on exams, I don't give them any of the works that they do by hand for homework. I don't. And basically, I use a lot of small projects across the semester. And at the end of the semester, I would ask them, maybe if I have it, I can share what I do at the end of the semester. I will give them a whole description of what they have to do, synthesizing a couple of topics. They cannot choose everything. Choose data of interest to you, and use 1 or 2 algorithms from the class, and like the introduction, the reason, the mathematics used, run the software, conclusion, etc. Like any final project. So I have small projects that I grade, and I don't know if I call them projects, small applications, They have to enter the data, and they have to clean the data, and they have to have their own. So I told you many people put their own image to do, for example, singular value decomposition. So I know that they did their own work. But yes, basically in this class, I don't do a lot of just testing of, no, applications. And several small ones, and towards the end of the semester, after the midterm, I start talking about long-term project.
So there's a question related to the data collection side. So when students are developing their own projects, how do you kind of give them guidance on how to choose data or how to work with the data that they found? You know, like
Okay.
where to get it or how to...
So cleaning the data and getting the data takes a lot of time in my office. I give them sources like Kaggle, like the government site, you know, like they go to, you know, from Corona, they collect, you know, Corona, they collect, you know, like I give them hints where to go, you know, NOAA, if they are interested. So I don't know if I should put this reference from the data where I send the students. I can add it as one of the slides. I don't have it right now. I can, you know, find it in my laptop. I give them sources to start with, and this is how they can get ideas. Yeah, you know, like I remember there was one time in the Gulf, one student did that. There was an oil spill, you know, in the Gulf of Mexico, maybe 10 years ago or something. So people collected data about, you know, clarity and density of the water because NOAA was publishing, you know, daily data. And they used, you know, I'm saying what they did. Some students use that, you know, about the density, clarity, what else? Oh gosh, I should remember, you know, a couple of factors, and they collected that for a long time. So preparation of the data takes time. And this is one source, for example. They were interested, they found the data in the NOAA and OAA, national, it's the weather. It's the weather. Yeah. So I choose Kaggle, but the data is not as easy from Kaggle. And I use, you know, the government site. There is govdata.com where you can find all kind of data. Sometimes if the data is very large, I will tell them, you know, like scale it for 1 month. Because my objective here in the course, I cannot do much. It's not like research thesis. I tell them, you know, reduce it to a month. You don't have to do 10,000. But, you know, most of the data is saved as a CSV file, and MATLAB can deal with these files. So they don't worry about, you know, how large is the data, because once it is already done with the government site as Excel sheet, whatever it is, it's not hard to run it, but they have to understand, what does it mean? What is it? This is more important than how large is it.
Mm-hmm. Yeah, we did have a request for you to include that slide on your...
I will.
Sounds good.
I will send it to you.
So any other questions?
Okay, thank you. If we're done, I appreciate you spending this time this Friday afternoon listening to me. And I hope that you didn't feel like you wasted your time. Thank you so much.
Yes, thank you. And thank you, Alam. Yep. And like I said, we have another webinar next week, same time, focused on science gateways for computational chemistry and biology. So thanks, everybody. And have a good weekend.
Can I download? Give me a minute. We're closing now, or
yeah.
I want to download